Okay, I want to finish up some stuff with Coulomb's law today. So Coulomb's law describes an attraction between things of opposite charges. And the strength of the attraction, so I'm just going to call it the attraction strength, is defined by this equation here. K is a constant. You don't really ever have to calculate anything with this, but if you can use this kind of qualitatively and figure out, well, if I change one of these numbers, how is it going to affect the strength of the attraction? That's what you want to be able to do. So Q is the charge of particle 1. So this is going to be something like K. And Q2 is charge of particle 2. So that's this one here. R is the distance between the two nuclei. So if I take these two particles and I look at the internuclear distance, the space between the nucleus here and the nucleus here, that is R. It tells me that if R is smaller, if it gets closer together, this is a smaller number, this attraction is going to go up. Or if R gets bigger, then this attraction is going to go down because my R gets bigger. Or Q, if my Q gets bigger, so if I change the charge, I can also make the attraction change. Or if I change the charge here, I can make the attraction change here. So we're going to look at a couple scenarios of how this plays out. Okay, Q here, I'm just going to say Q for this one is going to be a 1 charge, so plus 1. Q here is going to be also 1 charge, a negative 1. When you multiply them together, this doesn't really matter what the charge is, if it's plus or minus. It's just the number. The number is what really matters. It's if it's 1 or 2 or 3, it tells it the strength of that attraction. So let's take a look at two substances here. KCl, we looked at before, KCl. Let's say it has some kind of strength of attraction. And now I want to look at something like rubidium chloride. So we looked at this in class. Rubidium is a little below K on the periodic table. So rubidium is going to be bigger. Okay, chlorine is still the same size. And so now what's happened? Well, has Q changed? Q1, Q2. And we can see that Q is still the same. So the charges have not changed. However, what has changed is R. Okay, so R is here. That's my internuclear distance. And here R is this distance, but here R is this distance. It's bigger. So what does that do to my equation? So I'm looking at my equation. The strength is K times Q1 times Q2 over R. And so when we describe how the strength changes, it's important that we talk about both charge and internuclear distance. So charge and internuclear distance. So a lot of your scoring on the AP test is going to be how you describe these things. And for rubidium chloride, has the charge changed? No. So there's no change in charge. So we can say the charges are the same as they were in KCl. So charges are the same as in KCl. They're both plus 1 or minus 1. So they're all 1 charges. But the internuclear distance, R, has gotten bigger. So it's gotten bigger. And because they're farther apart, R, because it's in the denominator, this makes the attraction strength, so it makes the Coulombic attraction strength, strength of attraction, weaker. Okay? because they're farther apart. They can't hold on to each other as tight. And so that's going to affect a lot of things. It's going to affect the melting point. So the melting point here, you can imagine, it's going to get weaker, so it's easier to melt. And boil as well. So that's how you describe internuclear distance changes. What if I have something like KCl and calcium sulfide? So Ca is here, so now I moved in a little bit. And sulfide, Cl, is right next to sulfur. So I moved in a little bit. They're in the same rows as they were. So so if you look at this, K and Ca is going to be a little smaller. I don't know if you remember that from the last year, but if you go across the periodic table, things get smaller. So K and Ca gets a little smaller. S is a little bigger than Cl. Okay, so it's going to be a tiny bit bigger, but not much. It's going to be pretty much the same size. So there's not a whole lot of difference in size. But what do I know about the charge of Ca? Well, it's in the second column. S, second to last column. So this is now going to be +2, or 2 plus. This is now -2. And so there's not a lot of change in internuclear distance. So R is pretty similar, okay? So if I look at my equation here, the strength is K times Q1 times Q2 all over R. And if I said, well, the internuclear distance is pretty similar to KCl, because Ca and S, so Ca in the same row as K, same as S, in the same row as Cl. But what has changed? The Q's. So Q, the charge, Q1 and Q2 have now increased. Okay, so it have increased to +2 or -2. So we've doubled the charge. Because we've doubled the charge, what's going to happen to my strength of attraction? Well, this thing here is going to have a much higher strength of attraction. Because we've increased the charge, the strength, the Coulombic, AP readers love it when you use the word Coulombic. The Coulombic strength, or Coulombic strength of attraction, or just Coulombic attraction, is higher because of this right here. Okay, we've doubled the charges, and so that's going to make this strength a lot higher. So melting point for CAS is going to be much higher. It's a lot harder to pull that apart, and any other properties that go with it.